All right. Talk me through it.
Okay, so I'm going to say that I think I know the answers for this one. And let's start with the first one. So R1 equals minus R2, which you'll notice they are equal and opposite. And in fact, if you add them up, that is, you sum them, you end up with 0. So I'm going to say that's a zero-sum stochastic game.
Nice.
For 2, basically you're saying that for all intents and purposes, there's only one agent, which just makes it a regular Markov decision process.
Yeah. So isn't that interesting that just by making the other player irrelevant, then that's what an MDP is. It's like a game where the other players are irrelevant.
Yeah, which both of my children are like that. But okay, I think that's pretty cool. And in fact, I'd be right in saying that R2 doesn't have to equal to 0 as long as it just equals to some constant.
Yeah, constant. Actually, depending on how you think about it, we could just ignore the whole R2 thing and just say that as far as the first player is concerned, since the second player really has no impact on anything, it doesn't matter. But the reason I put that in is I got kind of scared that, like, I feel like if I lived my life and knew that my actions affected the state and my rewards, but they were also affecting the rewards of somebody who didn't matter, like, I feel like that would actually still have an influence on me.
Sure, but then the way you'd get around that is you would say, well, your R1 is actually equal to your R2.
Oh, so if I had gone like that, wouldn't that be the case then that we're saying? Oh yeah, I see that the second player is irrelevant, but the first player may be relevant to both.
Right.
Yeah, okay, I like that a little bit better.
Yeah, I mean, once again, it all boils down to changing the rewards. Okay, and so given A and B, I know the answer to 3 must be C, unless you're tricking me. And it could be A or B again, which I suppose you could have done. You didn't say they were mutually exclusive. So let me actually argue why it would be C. Well, there's only one state. And since you're in a stochastic game and you're going to be continually doing this, it means that you're basically doing the same game over and over and again. So it's a repeated game.
Yeah. So in particular, the actions impact the rewards, but they're not going to impact the transitions because you're always just going to go back to where you were. The discount factor plays the role of deciding when the game is going to end stochastically.
Mm-hmm.
And so, yeah, it's exactly a repeated game. Like, this is the one I feel most comfortable about because this really does recover that same model that we've been talking about.
I like it.
Cool. Now, given that we actually are now in a model that generalizes MDPs, it would be nice if we could generalize some of the things that we did with MDPs, like Q-learning and value iteration, to this more general setting. So that's what we're going to try next.
Cool.